Nice. Hello, everyone. So I'm here today to talk about the survey of artificial intelligence for card games in general and its application to the Swiss card game Jass. I have to say a bit disclaimer, this work has been done by a master student of mine, Joel Niklaus, which unfortunately is not here today because he's traveling in Singapore. But let's get this started. So first of all, perfect information games, so games where we know everything about it, so the state is clear, such as chess or Go. I've witnessed great successes in the last decades. We started with Deep Blue back then, already some decade ago, and then most recent or more media coverage is for AlphaGo and AlphaZero, which beat professional players on chess and on Go. And the interesting thing about this is that at this point, we have an AI capable of winning every single game and always, even against the most powerful human. And this is possible because the AI has just an advantage in terms of computational power. It can just look ahead, compute almost all possible moves, so to speak, and say, hey, OK, this is the best move to do. I know it, because I know the game, I know the board, how it looks like, and I can take the best decision. This is not possible if some information are hidden, like in card games, like in poker, where you don't know the cards of your opponent, so you can't take the best possible decision because you will need to know the other cards to take it. Now, why are these hidden information games important? Is because we like to talk about games and playing, but at the end of the day, the technology that will solve these games can also be generalized and apply to real-life problems. There are very many applications, but for instance, energy optimization in data centers or surgical operations. When a surgeon operates, there are a lot of unknown factors which the surgeon estimates with his professional proficiency, but it will be nice if an AI could help surgeons and to navigate difficult operations. Or in business, when you have negotiations, a lot of information is hidden in your counterpart. So there are real case applications which are very interesting to tackle. Now, it's not novel, right? There is already a lot of AI work done in this sense. And again, recent breakthrough have been witnessed. For instance, we have the OpenAI 5, which plays Dota 2. It's a computer game where two teams compete for supremacy in an arena. Or we have Libretus, which plays poker. And we have also, very recently, AlphaStar, which plays, again, another computer game, StarCraft 2. This is from DeepMind, so from Google. These are big companies. They developed this software. They are extremely good, yet they are not undefeatable, with the small exception of Libretus, which reached almost perfect solution for poker. That means that playing against this AI will not be a very good idea if you will bet your own money, because it's almost guaranteed that you will lose. Now, what is the next challenge? I'm here today to propose to you the next challenge is Jass. Jass is I guess you're familiar with it. It's a very traditional, popular game in Switzerland. It's a card game. It's often played with 4 people, which competes in 2 teams of 2 against each other. And of course, there is information. You know your own cards, you don't know your opponent's cards, and you don't know your partner cards. This is very important. It is sequential because everyone plays a card at a time, and it's non-cooperative because we have 2 teams competing. And it's also finite. This is interesting because you know it's going to last 9 turns. You have 9 cards, you play 9 times, and that's it. And it's a constant sum. It means the sum of the points in a game is 157, and they're going to be distributed among the 2 teams in all games. So an important aspect of playing Jass, for those who already played, you know it. For the others, is like you need to cooperate with your partner. Otherwise, you're not going to go very far. This cooperation implies that you kind of coordinate and synchronize on what to play and how to play, except you cannot talk to your partner. It's forbidden by rules. So you need to communicate what is your idea, what is your strategy, what cards you have by playing. One common example is like, as you see on the slide, if player 1 starts with an ace and player 2 follows, player 3 doesn't have this kind and plays the 6 of diamond. That signals to player 1, hey, look, don't play diamonds again because I'm probably not strong in that. Now, this is not even sure. It's just an unspoken rule, so to speak. It's like a common agreement that experienced player use to try to signal the partners. But then is the question, can an AI learn to signal stuff to humans, to pick up these subtle techniques and strategies to play the game. And then this idea of proposing Jass, I mean, we are not the only one which looked into this direction, and also DeepMind from Google came to the conclusion, okay, computer games are fun, but we want to tackle something which implies cooperation, and probably they don't know Jass so much, or they're not so fond of it. They came up with Hanabi. It's another card game which you need to cooperate to win, but they share a lot of similarities, the two games. So basically, if you would have an AI which succeeds in one, you could easily translate it to the other and say it works well for the other. They are both multiplayer, they both have it in information. Just the difference is that in Hanabi, everyone is playing together to win, and in Jass, you want to beat your opponent. So that's why Jass it's suitable to do it. Now, our contribution in our paper, we made a survey of what has been done in the AI field to solve hidden information games, which we have the four major categories. The first is rule-based algorithms, evolutionary, reinforcement learning, and Monte Carlo tree search. The two latter, so reinforcement learning and Monte Carlo tree search, are the most prominent nowadays. And then we started analyzing how can we use these techniques to play Jass. Now, just a brief overview. Rule-based systems are like, in a way, glorified decision trees. It basically implies if you are in a situation, do this. And this requires human knowledge. Like I explained before, these rules are kind of human knowledge. I know the game, I know what is good and what is bad, and I tell you, if this situation shows up, you should do this move. So if these are the cards, play this one because it's a good idea. But this requires that you know what is a good idea and what is a bad idea. And this works well in small games, in tic-tac-toe or so, but for more complicated game, it quickly spirals out of control, right? Then we have evolutionary algorithms, which builds up on this survival of the fittest paradigm. It's inspired by biology, where basically the idea is to have a population of solutions, and then you have them compete for their survival, and then you will iterate this process, and over time, you will refine the quality of your population with offspring and the like. The two examples I bring you here today is blackjack. You can have a population of strategies, then you have them play for 1,000 iterations, and then you measure how much money did you make, and this amount of money is how good your strategy is. And then you select the best, and you start new populations, and you do it again and again. And after some time, you are satisfied with the amount of money your strategy is doing. Another application, here I bring Hearthstone, but you can imagine any deck-building card game where you have a lot or thousands of cards, and you have to select 30, in this case, to bring into your game. And then the question is, which are the 30 best cards to select? Here you can easily see the fit. We call a population the 30 cards. We make many samples, and then we have them play. We look how good they are, and then we iterate this process. This works well. It could be applied to Jass, but it's very impractical. What can be applied to Jass is reinforcement learning. Reinforcement learning is a paradigm which is there really since a long time, and there are many variants and many algorithms, but the core idea is that you have an agent, which could be an AI, which could be a human, and you have an environment. In this case, it would be, for instance, me in this environment, and then I can perform actions. For instance, I take a step forward. Cool, and then I can see the next state. I am one step forward, trivial, and the reward. In this case, I don't really get a reward for that, but if my goal was to leave the room, I take a step, I'm closer to the room, I am having a positive reward. If I take a step in the opposite direction, I am further from my goal, and I get a negative reward. In Jass, that will mean that you play a card, you make that many points, that's good. You make no points or only fewer points, that's a negative reward. And the to-go choice nowadays for reinforcement learning is the counterfactual regret minimization, which is a complex algorithm. I will need hours to fully explain it, but the core intuition behind it is that we have this agent, our AI, playing a game. So you play a game of Jass. Or let's make an analogy with football, right? You have your team which plays a game, and then you have the coach which takes the players into a room, shows them the replay of the match, and then tells them, you see here, at the 17th minute, you should have passed the ball because your teammate was good to score, or there you should have run back further, or this kind of feedback. And then the players know, okay, I should have known better. In this situation, I should have done that instead. And then you play the game again. And then you look again the replay, and then you play the game again, and so on and so forth. And we are talking this millions of times or billions of times. And this has the particularity that you don't need an opposing team to learn this algorithm. You can have the AI play against itself. And in the beginning, it's going to be random. It just makes random moves. And then you tell it, here you should have done better. And you improve. And over time, it will learn literally itself what is a good move to do and what is not a good move to do. Now, a desirable property of this algorithm is that eventually the average of the strategy that it comes up with is going to converge towards a Nash equilibrium. This Nash equilibrium means basically that you perform on average as good as possible. For instance, the Nash equilibrium for the tic-tac-toe game, it's knowing how it works. And if you have two good players, you know you're never going to win in tic-tac-toe. You know it gets boring because every time you end up tying, because you have a Nash equilibrium strategy. This algorithm aims to find this strategy for more complex scenario than tic-tac-toe. There are very many different variants of this algorithm. There are several research teams that are building up on this. And this is the algorithm that Libretus leverages, the CFR+, and they came up with a near-perfect Nash equilibrium. This is why I said in the beginning, don't play poker with your money against Libretus, because it plays almost as good as you can. So your best bet against Libretus is to tie against it. And they tested it by putting a lot of professional players into a room with the AI for 2 weeks, and they measured 120,000 games, and it almost always win, and barely ever lost. So they're probably very rich right now. Another approach to solve problems a bit tangentially related to reinforcement learning in this scenario, we have Monte Carlo simulation. Now, these slides I show just to refresh the Monte Carlo approach. It's to approximate something that we cannot really compute perfectly, like we have now. We don't have perfect information, so we will approximate it. Basically, that's it. You try something at random for many times, and then you measure the probability of something happening because you tried so many times that you know more or less what's going to happen. You don't know for certain. You're working with probabilities, but you're trying to estimate what is the real distribution behind it. And in Jass, we would model it like following. We have this simple algorithm. We have the selection phase, which is at the beginning. You look at your cards, and you choose which one you're going to play. Now you choose one, so you select it, and then the expansion is just playing it. In our case, it's just taking the card and putting it on the table. And then we need to know, OK, what's next? And then we simulate what the other players are going to do. And you can do that at random. You just assume, OK, this player is going to play that, that, and that. And we go on until the end of the game. As I said in the beginning, it's a finite game. It's 9 rounds. This is good because we can simulate the game until the end. And then we look, how many points did we do? And we backpropagate this score through our search tree. So at the end of the game, we say, OK, I played the ace as first card on the first trick. I scored that many points. Now, which card will they select next? And now you're like, yeah, OK, cool, but you simulated your opponent. And this is a tricky step, because to begin with, you cannot know what your opponent will really play. And you don't know which cards they have. So you're going to guess what cards they have and guess what cards they're going to actually play. And it's very unlikely that you're going to guess correctly. So here kicks in the Monte Carlo thing. We try it many times, and then we will just assume, OK, I tried it 10 million times. Most of the times, this was the outcome. So statistically, I choose that this is the best card to play right now. You don't have guarantees. You're just approximating what it's going to be looking like. There are many variations of that, too. You can very well imagine there is plenty of literature on that. And now, very, very recently, some months ago, some teams came up with the Monte Carlo sampling for regret minimization, which is basically putting the Monte Carlo research on top of the regret minimization that we showed before. So they are starting to merge the two branches. Now, as I said in the beginning, the Monte Carlo and the CFR, the reinforcement learning, are the most successfully used to card games. CFR, so now it's used only in poker, but they are starting to apply it to other scenarios. And it has the particularity that it approaches this Nash equilibrium, so it doesn't lose, but it also doesn't exploit your opponent. This happens all the time between humans. I know in my opponent, I'm going to try to do something to beat him, especially in football. You know the team you're going to play against. You know they have a good goalie, or you know they have this good player. You play against it. So you tailor your strategy to your opponent. CFR doesn't do any of this. It totally disregards what your opponent is. It's saying, I do a good game. I don't care who I play against. This is my play style. And this is good in general, because if you have a good play style, you're going to perform better, good against almost everyone. But in retrospective, you don't exploit your opponent. Maybe they have a particular weakness, and you're not taking advantage of it. And this is exactly what the Monte Carlo tree search is doing. It's looking for weaknesses and jumping into them, because with this simulation, it just looks, ooh, we are in this situation, statistically this will happen, and it will find this weakness in your opponent. But you have no guarantee that the solution it came up with will work good against another opponent. So these are a bit the two sides of the medallion, right? In one case, you have a good defense, plays good in general, and in the other, it's I'm going to fit to my opponent and exploit his weakness if he has any. And so the choice depends on what you want to do. You want to have something that works good in general, or you want something that just wins a tournament. If you want to win a tournament in particular, you might want to go Monte Carlo. If you want to have, for poker, winning in general and make money, probably CFR is your choice to go. So in our preliminary results, we implemented a Monte Carlo tree search bot, which won there was a Jass competition here in Switzerland 2 years ago, and our bot now competed against the winner of the competition and beat it. And you can play against it on the link you see on the slide. It's a website, you can go there, you can play with 3 other bots, or you can play with a friend of yours against the bots, or you can play with the bot and against your friends as you like. And we are just registering all the games and learn how good is the bot performing. And so far, we tried it amongst our friends and communities. The bot is consistently beating human players. So we have no final results, but it seems that it's performing very well. So as a conclusion, the rule-based algorithms with these decision trees are replaced nowadays by most popular Monte Carlo tree search and reinforcement learning algorithm. The Monte Carlo tree search is going to find good strategies and quickly, but it can be exploited by someone else because you don't have guarantees that it's going to be a good strategy. You just know it works against this opponent. And reinforcement learning tries to find something general, but is not going to leverage your opponent. And Jass is a hard game, and it's then suitable for trying to develop these new AIs. And our preliminary results suggest that Monte Carlo tree search can beat humans. And that will be it from my side for today.